All right, let's take a look at our lesson for today. So today we are revisiting accumulation and definite integrals. We looked at accumulation actually in general back in Unit 6, but we're going to keep working with it and specifically with the calculator. So let's kind of focus on our first question. So we have a storm's washed away sand from a beach, causing the edge of the water to get closer to a nearby road. Okay, that's the scenario. The rate at which the distance, so I like to, as I'm reading, I like to circle really important words. Like this is a rate, the rate at which the distance between the road and the edge of the water was decreasing. And now this is important. They're saying it's decreasing. And this is the equation for our rate. All right, so it's in feet per hours, t hours after the storm began. The edge of the water was 200 feet from the road when the storm began. If the storm lasted 4 hours, how far is the water from the edge of the road? All right. So we talked last time about two different methods on deciding how to do the fundamental theorem, or method one was basically putting the 200 out here. This is a little bit of a trick though. So it says that this rate is decreasing. So we're starting at 100 feet from the road, but we need to decrease. We need to subtract the integral of the rate. So if I integrate a rate, I get a position, right? And the position, so this rate has to do with the distance between the road and the edge of the water is decreasing. It has to do with distance. So the rate that it is changing. So when I integrate, I'm going to integrate from the starting time to 4 hours, because that's what they asked, of the rate. I would recommend that instead of copying this function down, that you write the name of the function, which is r of t. That way, you don't have the issue of perhaps copying it down incorrectly and causing a copy error. So we would prefer to use the name. All right, so I would put this in my calculator. Just like this is 200 minus the integral 0 to 4 of this equation, this rate, and that's going to give me 196.937 feet. Now, let's say that we didn't realize that it was decreasing. Let's just pretend, okay? Let's pretend that we didn't realize, or we missed the fact that it was decreasing. If I put a plus there, I would get like 203 something. What would tell me something is wrong? We need to be aware of what we're doing, right? What would tell me that something is wrong? It's over 200. And so when we see that, if you accidentally put plus and you get a number that's bigger than 200, you should say, oh, wait a minute. That's really what's supposed to be decreasing. And so we put the minus there. So let's just talk about how we would fix it if we, didn't recognize it was decreasing. Does that make sense? So just be careful that what you get is what you're expecting to get. Since they said that it was decreasing, we should expect to get a smaller number. If we got a bigger number, then it has to do with this. We accidentally added this instead of subtracted it. Okay? Is everybody all right with that?
So just basically what you put in the calculator is 200 minus the integral negative sign and then 4 st.
Oh, good question. No, so this is what I would type into my calculator. I would type it exactly like this. I would type it as e to the negative sign, and I would use x in my calculator and not a t, and then it makes me do the dx. So I would type it in my calculator just like that with the variable, with the x and the dx, and then that would give me the 196.937. Okay, thank you. Good question. Any other questions? Okay, let's look at our second one. So on the second one, let's see, we have a store having a 5-hour sale. The rate at which the shoppers enter the store, t hours after the sale begins, is modeled by this function. So this, I like to, underline things that are helpful. That's the rate. And the rate is, this is the rate. This E is a rate. And here's my units, shoppers per hour. I'm just kind of highlighting the things that I need to be sure to go back and pay attention to. When the sale starts, there are already 70 shoppers in the store. So this is going to be significant. We need to recognize we've already got 70 shoppers there. Okay. Write, but do not solve an equation involving an integral to find the time x when the number of shoppers in the store is 200. Is 200 means is, we know from our experience with word problems, that means equals. So apparently I'm supposed to say something with an integral equals 200. That's what I'm supposed to say, okay? And we're going to assume that nobody leaves the store. So we're starting with 70 shoppers, and this is the rate that they're entering. So if I integrate the rates they're entering, I will get the number of people entering. We okay with that? If I integrate the rate that they're entering, I get the number of people entering. So I'm going to add the rate. So we're going to do the integral from 0 to, and it's x. They're telling us to say, they're not really telling us when they want us to do this. They just want us to set up some kind of an equation that would allow us to do this, to find out the x. And then we don't know, the equation is e of t, dt, and we want to know when that would equal 200. So this would be the equation that we would use to solve that. And they're not asking us to solve it. We don't even know what e of t is, but this is how we would set that up. Okay? Is everybody okay with that? See how the x is just, we can say, oh, well, is it 2 hours or 3 hours? I don't know. We would need to actually solve for this number, right? We don't know what that is. We would use our calculator to solve for that number. All right, so let's look at the next page. So we have water being pumped into a tank at a rate. Here we go. Let's see what we have. We got a rate modeled by R of t, and our units are liters per hour, where R is differentiable and decreasing, okay, on the time 0 to 8. Selected values of this function are shown in the table below. And they're giving us an initial condition. We have to pay attention to this. At time t equals 0, there are 5,000 liters of water in the tank. So that's important to know. All right, so that's our scenario. Let's see. So it says, what does the integral from 0 to 8 of r of t dt represent? So this is a question that's important, conceptually. We need to understand what it is we are finding. So if R is the rate that water is entering into the tank, and we integrate R, if we integrate the rate, we get a quantity, right? So if we integrate the rate, we're going to get how much water there is. You with me? Okay, so they're asking us to explain it, and when we explain it, I think we've talked about this before, somebody came up with an acronym, NUT. We need to be sure that when we're explaining things like this, we add all that in. That is a noun. We need the noun, which is what's going on. We need units, and we need time. We need those three things to get full credit for our explanation. We need all three things. Okay, so just make sure that when you write explanations, you include all of those three things. So what's going on? This is what the noun is. This is the amount of water. So the amount of water, and I'm going to write the units in liters, pumped into the tank from t equals 0 to t equals 8 hours. So I go back and double check. I've got, here is my noun, my amount of water. That's my noun. So here's I've got a couple of different units. I've got units here and there. Those are my units. I've got my time period here. So we've got our time. What's our time? And we basically handle, we have the nouns, the units, and the time. So we're good. Okay? Now they want us to actually estimate that integral, the integral from 0 to 8 of r. So we're going to estimate how much water was, pumped into the tank using a left Riemann sum. Oh, left Riemann sums, yay. Okay, so I'm going to do Riemann sums. Personally, I have to write out a number line. I know y'all are, don't always have to do that. I really am pretty, I need to see, I'm very visual. I need to see what's going on. Okay, so I'm going to pretend, we've got some, I'm not even trying to be accurate. We've got some rectangles here, right? I'm just making some rectangles. We got some rectangles. And so we want to use the left Riemann sum. So we want to use the left side of the rectangle to represent the height of the rectangle. Y'all remember that? The left side represents the height. So I'm just going to, I'm going to make, this is the left side of, we're going to do the left side here. That's the left side of this one. That we're going to do the left side. We're doing the left sides. Okay, we're doing left. All right, so we write out integral from 0 to 8 of r of t dt is approximately, if you wrote equal, it would be okay, but it really is approximately. So what do? We have to show the products and the sums, okay? I can't just write down, I can't do this in my head. I'm not allowed to find the area of that rectangle, rectangle in my head and just write them down. That's not a thing. I have to actually write it out. So the height of this first rectangle would be at 0, would be 3,000. And the width of this first rectangle is 1 plus. Okay, let's go to the second rectangle. The height of this second rectangle would be represented by the left side, which is 1, so 2,500. And the width of this rectangle between 1 and 3, the width is 2 plus. We doing okay? Okay. The next rectangle, the third rectangle, the height of this rectangle would be represented by this height at 3, which is 2,100. And the width of this third triangle between 3 and 6 is 3. Got one more rectangle. So I've got the height of this rectangle. It's going to be represented by this height at 6, which would be 1,500. And the width of this last rectangle would be between 6 and 8, so that's 2. Okay, so this part right here is called the products and the sums, and it has to be written like that. You could actually stop there and write the units and be done. You could. It would be okay. I went ahead and, put it in my calculator. This is a calculator problem. I went ahead and put it in my calculator and made it do all the calculations. And it turned out to be 17,300, and our units is liters. So that would be our answer. Again, if you wanted to, because this is all numbers, I couldn't have said R of 8 and box that. That's not okay. But if I have just straight numbers like this, I could totally have written liters. So this whole thing is liters. I could have written liters like that and just box that in, and that would have been just fine as well. Okay? Either one of those is fine. Part C, based on this estimate, how many liters of water are in the tank after 8 hours? That sounds like a trick question, doesn't it? Because we just found how many liters were in there between 0 and 8. Why is that not a trick question? What do they want us to recognize? What do they want us to recognize? What did they tell us at the beginning? That it already has 5,000 liters in it, right? It's not an empty tank. It's not empty. It already has 5,000 liters in it. So based on the estimate, how many liters of water in the tank after 8 hours, it would be the beginning amount, which is, 5,000 liters, plus the amount that was pumped in during the 8 hours, that's going to tell me how much is in the tank, right? That's what that's going to tell me. So I would add those together. I get 22,300, and that's liters. Okay, are we doing okay? All right, so keep in mind, we need to refer back to the prompt and make sure that we're, remembering all the things that it told us and not just automatically put down 17,300 without thinking about it. Okay, so there was water starting out. Okay, we have one more two-part question. We ready to move? Keep moving? We okay? All right. On your copy, this part right here was, I mistyped it. If you would fix that, and on the copy that you have, I didn't have a chance to fix it before you got it. What it should say is water is pumped into a tank at a rate. No, it shouldn't say a rate. Is pumped into a tank at a rate modeled by W of T. No, I didn't fix it. It's not a rate. So water is modeled by W of T, the number of liters of water in the tank at a given time T measured in hours. It should say, and so both of ours is messed up. It should say the table of values represent W of T. So this first part we want to cross out. The table of values represent W of T, which is the number of liters of water in the tank at a given time T measured in hours. Okay? Yes, I got a little crazy on my typing. I got a little crazy. So the table of values represent W of T, which is the number of liters of water in the tank at a given time T. Okay, so here we go. So this is, and if you're not really sure, you can also look at the units, right? This is in liters, right? This is a quantity of water, right? W is a quantity of water, and T is in hours. Units are helpful. So if we're integrating the derivative, the rate that the water is changing, what would we get? If we're integrating the rate the water is changing, we would get the amount of water. Yes, the amount of water. So what does that represent? It represents the amount of water in liters. Let's put our units in there. In liters pumped into the tank. This is like a part 2 of the one that we just did. Pumped into the tank from T equals 0 to T equals 8, and our unit is hours. Okay, so do we have our noun? Yeah, we've got water being pumped, noun, units. We've got liters and hours and time. We've got T equals 0 to T equals 8. So we have all of our requirements. Okay? Now they want us to find the integral of W prime of T dt. Well, we don't have the equation. If we had the equation, we would do the antiderivative, right? We would do the antiderivative if we had the equation. Well, we don't. So there must be a way. Let's think about this. So if I'm integrating from 0 to 8 of W prime of T dt using fundamental theorem, that would be the antiderivative of W prime would be W, right? So W of 8 minus W of 0. That's really what I would get. That's what the fundamental theorem tells us, right? So do I know what W of 8 and W of 0 are? I do, don't I? Aren't they on the table? So I can just use those values off the table. So here's W of 8, there's W of 0. So W of 8 is 22,000 minus W of 0 is 5,000. And so And what are we finding? We're finding the amount of water in liters pumped into the tank from t equals 0 to t equals 8. And so this is 17,000 liters. Okay. All right, we all right?